Okay, hi everyone, welcome to VSPG. Today we're hearing from IvánGarduño. He's talking about atmospheric chemistry and climate variability across the oxygenation of the atmosphere. Jim, please go ahead and introduce Daniel for us.
All right. IvánGarduño is a PhD candidate at the University of Victoria's School of Earth and Ocean Sciences. His research examines the interplay between climate, atmospheric chemistry, and geological processes throughout Earth history with a focus on modeling atmospheric oxidation events. Daniel combines a strong background in earth science with technical expertise in climate modeling, programming, and machine learning. His recent work examines how climate variability influenced atmospheric oxidation during the Great Oxidation Event. Take it away, Daniel.
Thank you so much for the introduction, and thank you for the opportunity to present my work in this seminar. I am very happy to be here. In this seminar, I will present some of the work I've been doing in my PhD in collaboration with my advisors, Colin Goldblatt and Anne-Sophie Yam at the University of Victoria. And this work has been mainly focused on understanding how climate variability could have affected the evolution of oxygen across Earth's history. But I have also been working in trying to understand the atmospheric chemistry of the oxygenation of the atmosphere. And by that, I mean understanding how the interaction between different gases changes when you go from an anoxic atmosphere to an atmosphere that is rich in oxygen. So these are going to be the main topics of my talk. This is the outline for the talk. First, I will provide some background. Then I will talk about the effects of climate variability on the oxygenation of the atmosphere. And in the final part, I will talk about the atmospheric chemistry of the Great Oxidation Event and how climate variability could have affected it. So this plot here on the left shows the current atmospheric composition and thermal structure. The y-axis at the top shows temperature, and the x-axis shows altitude. So as you can see, temperature decreases with altitude in the troposphere until about 10 kilometers. And about 10 kilometers, temperature increases with altitude due to the influence of ozone in the stratosphere. And above the stratosphere, temperature decreases with altitude. The other x-axis at the bottom shows the mixing ratio of different gases in the atmosphere. This is a volume mixing ratio, and throughout this talk, I will be presenting many plots with these volume mixing ratios. This is just the ratio of the number of moles of a gas over the number of moles of fire. And you can think of this quantity as the fraction of the atmosphere that is occupied by a specific gas. In the modern atmosphere, oxygen and nitrogen are the main components. These gases have mixing ratios of about 0.78 for nitrogen and 0.21 for oxygen. And these very high levels of oxygen in the atmosphere are very important. They are important for all animals, including us, because we need oxygen to do respiration and survive. But oxygen is important for other reasons too. One of these reasons is that thanks to the high levels of oxygen in the atmosphere, we have an ozone layer in the stratosphere that protects the surface against dangerous ultraviolet radiation. And another reason is that thanks to the high levels of oxygen in the atmosphere, some very toxic gases for us like carbon monoxide, methane, and hydrogen have very low mixing ratios in the atmosphere because these gases are oxidated in the atmosphere. So oxygen is very important in the modern atmosphere. But as you know, the atmosphere wasn't always rich in oxygen. This plot here shows an schematic of the evolution of the surface oxygen mixing ratio in the y-axis over time in the x-axis across Earth's history. And as you know, the atmosphere had almost no oxygen for a long period of time during the Hadean and the Archean eons. And it wasn't until the Proterozoic, around 2.5 to 2.3 billion years ago, that the atmosphere became oxygenated during the Great Oxidation Event. oxygen reached levels or mixing ratios of about 10 to the minus 4 to 10 to the minus 2 during this event. There is still some debate about the exact levels that oxygen reached during this event, but we are confident that oxygen levels were lower compared to today. And towards the end of the Proterozoic, oxygen increased again, and it reached levels that are more similar to what we see in today's atmosphere. The boxes here at the top show important events for Earth's history, and the more colored a box is, the more likely an event happened by a given point in time. For example, it is likely that oxygenic photosynthesis evolved before the Great Oxidation Event sometime in the Archean. And the evolution of oxygenic photosynthesis was the ultimate cause of the Great Oxidation Event. During the Great Oxidation Event, the ozone layer formed because this was the first time in Earth's history that the atmosphere contained enough oxygen to sustain an ozone layer. However, the ozone layer may have not been as developed as it is today. The eukaryotes evolved sometime in the Proterozoic, and the animals slightly evolved towards the end of the Proterozoic. So there seems to be a direct relationship between the amount of oxygen in the atmosphere and the complexity of life. So it is very interesting and important to understand how the oxygenation of the atmosphere happened. So now I will talk about the effects of climate variability on the oxygenation of the atmosphere. The Great Oxidation Event occurred around the same time of these global glaciations called the Huronian glaciations. The main line of evidence for these glaciations comes from glacial deposits in different parts of the world. These glacial deposits look like these rocks here. These are diamictites from the Huronian supergroup in Canada. And there are several glacial deposits in different parts of the world, and some sedimentologists argue that these glacial deposits are correlated. So this provides evidence that these glaciations were very widespread. Also, there is paleoaltitude evidence in some of these glacial deposits that suggests that these deposits were around the equator, providing evidence that these glaciations may have been global in nature. And these glacial deposits are on top of carbonate deposits, as we can see in the left bottom picture here. And this suggests that these glaciers were around sea level. So it is likely that the Earth was completely covered in snow around the time of the oxygenation of the atmosphere. And this plot here on the left shows a 3D simulation of what the surface temperature looks like in one of these Snowball Earth events. You can see that the temperature is very low. We have surface temperatures of about 270 Kelvin near the equator and much lower temperatures near the poles. And these Snowball Earth events were likely terminated by the accumulation of greenhouse gases in the atmosphere provided by volcanism. So there was likely a rapid transition between these Snowball Earth climates to these moist greenhouse climates with a lot of greenhouse gases in the atmosphere. And again, this plot here shows a simulation of the surface temperature of the planet in one of these moist greenhouse climates. You can see that in these climates, temperature is very high. We have temperatures of about 350 Kelvin near the equator. And there is debate about the number of glaciations that occurred around this time. Some people talk about 2 or 3 glaciations, others talk about 4. But the point here is that there was likely a lot of climate variability around the oxygenation of the atmosphere. So it is natural to ask this question. Does climate variability affected the oxygenation of the atmosphere? And this is my research question. And to answer this question, I use a one-dimensional photochemical model. A 1D photochemical model is a representation of how the composition of an atmosphere changes due to processes like reactions, transport, or rainout. These models typically solve an equation like this one shown here. So if we think of a molecule of a gas in the atmosphere at a given altitude, this molecule could undergo a reaction with another molecule. And this reaction will affect the concentration of the gases involved in this reaction. This process is represented by these terms here in this equation. These are the chemical production and the chemical loss of a specific gas in the atmosphere. And these are normalized by the number density of air. Another possibility is that this molecule could be transported up or down in the atmosphere. And this process is represented by this second term, this equation. And finally, another possibility is that this molecule could be absorbed into as rain droplet and be rained out of the atmosphere. And this process is represented by this last term here. So all of these processes could affect the concentration of a gas in the atmosphere. And in this case, this equation is measuring the concentration as the mixing ratio. This is what this F is. So if we solve this equation over time and altitude, we could get an answer like this. This plot shows altitude in the y-axis and the mixing ratio in the x-axis. And we see mixing ratio profiles for different gases. We see oxygen in orange, we see methane in blue, and ozone in green. So solving this equation over time, we could see how these mixing ratio profiles change over time due to an external forcing. But if the atmosphere is in equilibrium or in a steady state, this equation will be equal to 0. And all of these processes will balance each other so that the mixing ratio profiles of all gases in the atmosphere will not change over time. So how can we use one of these models to create a simulation of the Great Oxidation Event? Well, one way of doing this is to vary the oxygen input flux at the lower boundary of the model. This plot here at the top shows the oxygen input flux into my photochemical model in the x-axis, and the y-axis shows the oxygen surface mixing ratio. The bottom plot shows the oxygen mixing ratio in the x-axis and altitude in the y-axis. So in this plot here, I am prescribing an oxygen input flux at the lower boundary of the model of about 10 to the 10 molecules per centimeter square per second. And if I integrate my model to equilibrium, to steady state using this flux, I get a steady state solution for oxygen that looks like this here. This is the profile of oxygen. You can see that this atmosphere has almost no oxygen near the bottom of the atmosphere. So this is what the profile of oxygen will look like in an atmosphere before the Great Oxidation Event. But if I increase the oxygen input flux into the model, and this increase in the flux could represent an increase of primary productivity, I could make the oxygenation of the atmosphere happen. So this is an animation that shows this process. You can see how as the oxygen input flux into the model increases, the atmosphere becomes oxygenated. And there is a flux at which we go from an atmosphere that has almost no oxygen to an atmosphere that is rich in oxygen, and this represents the Great Oxidation Event. This plot here shows the same plot as before, but I will show you ozone mixing ratio profiles in the bottom plot, so that you can see how the ozone layer forms across the Great Oxidation Event in this model. You can see that when we have the oxygenation of the atmosphere, we have enough oxygen to sustain an ozone layer, and the ozone layer just keeps developing as oxygen increases more. So I can model or simulate the Great Oxidation Event with my photochemical model, but I am interested in understanding the effects of climate variability on the oxygenation of the atmosphere. So I need a way to model climate variability. And the way to do this in a one-dimensional model is to change the temperature profiles of the model. So to model the temperature structure of the atmosphere, I chose to use a moist adiabatic temperature profile for the troposphere and an isothermal temperature profile for the stratosphere. This plot here shows what the temperature profiles that I use look like. We have pressure in the y-axis, which is equivalent to altitude, and we have temperature in the x-axis. So you can see that for this profile, temperature decreases as pressure decreases or as altitude increases. And this happens until we reach the temperature of the stratosphere, and then temperature is constant because I am assuming an isothermal stratosphere. And the rate of decrease of temperature with altitude in this profile depends on the amount of water vapor in the air. Because if we have a parcel of air at the surface at a given temperature and this parcel rises in altitude, as the parcel rises, it will expand because pressure decreases, and as it expands, the temperature will decrease. And as temperature decreases, there could be some water vapor condensation, and that could release latent heat, which will affect the rate of decrease of temperature with altitude. So if we had a warmer climate and a higher surface temperature, this profile will look different. This profile will look like this. And in this case, our parcel of fire will have to climb to higher altitudes to reach the temperature of the stratosphere. So in a warmer climate, we have a thicker troposphere. So this plot here on the left shows what the temperature profiles that I use look like. We have altitude in the y-axis and temperature in the x-axis, and the different colors show different surface temperatures ranging from 250 Kelvin in blue, representing snowball Earth climates, to 360 Kelvin in red, representing hot moist greenhouse climates. And changing temperature is very important for atmospheric chemistry because if you change temperature, that will affect the amount of water vapor in the atmosphere. This plot on the right shows the water vapor mixing ratio profiles corresponding to the different temperature profiles that I use on the left. You can see that as we go from snowball air climates in blue to hot moist greenhouse climates in red, the amount of water vapor in the atmosphere increases a lot. And increasing the amount of water vapor in the atmosphere can really affect atmospheric chemistry because water vapor is the main source of hydroxide. And hydroxide is known as the detergent of the atmosphere. Paul Crutzen coined this term to refer to hydroxide or OH because OH is the main oxidant of the atmosphere. So if we think in terms of concentrations, like oxygen and ozone are the main oxidants because these gases are the more abundant gases in the atmosphere, but these gases are not very reactive. OH has a lower concentration, but it is highly reactive. So it is the main oxidant of the atmosphere. So OH reacts with methane, with carbon monoxide, and other contaminants. So basically, OH kind of cleans the atmosphere of these contaminants, and that is why people refer to it as the detergent of the atmosphere. In the modern atmosphere, the main source of OH comes from ozone photolysis. So we have ozone photolysis in the troposphere and also in the stratosphere, and this ozone photolysis produces this very reactive O1D molecule that can split water to produce OH. So this is a summary of the way I am addressing my research question. So I am creating a simulation of the Great Oxidation Event using a 1D photochemical model. And to do this, I am increasing the input flux of oxygen at the lower boundary of my model. And I am also increasing the flux of methane because there is a close relationship between the input fluxes of methane and oxygen. So that gives me a simulation of the Great Oxidation Event. And then I repeat the same process using different temperature profiles to simulate climate variability. And that gives me an answer of how climate variability could have affected the oxygenation of the atmosphere. So here are my results. This plot here shows the oxygen surface mixing ratio in my model in the y-axis, and the oxygen surface input flux into my model in the x-axis. Again, the different colors show different surface temperatures representing different climates, going from 250 Kelvin in blue representing Snowball Earth climates to 360 Kelvin in red representing hot moist greenhouse climates. You can see that as the input flux of oxygen to the atmosphere increases, the concentration of oxygen increases, and there is a given flux in which we have the oxygenation of the atmosphere. And after the oxygenation of the atmosphere, we see that warmer climates have more oxygen, which is very interesting. This is another way to look at these results. The top plot shows like the same plot I showed before, but in the bottom plot I will show you oxygen mixing ratio profiles. And I just plot 3 different temperatures here. The blue line represents a Snowball Earth climate, the black line represents a temperate climate, and the red line represents a hot moist greenhouse climate. So you can see how the atmosphere becomes oxygenated as we increase the oxygen input flux. And again, after the oxygenation of the atmosphere, we see that warmer climates have more oxygen. This is the same plot, but here I show ozone mixing ratio profiles in the bottom plot, so that you can see how the ozone layer forms in these different climates. And it is interesting that after the oxygenation of the atmosphere, when we have the formation of the ozone layer peaks at a higher altitude in warmer climates. Here I show the methane mixing ratio, the surface mixing ratio in the y-axis, and again we have the oxygen input flux in the x-axis. So you can see that in the oxygenation of the atmosphere, there is a collapse of methane in the atmosphere. The concentration of methane decreases. And after the oxygenation of the atmosphere, we see that warmer climates have less methane. And this is the same plot, but here I plot OH. And you can see that after the oxygenation of the atmosphere, we have more OH at warmer climates. And this makes sense because at warmer climates, we have more water vapor in the atmosphere, and water vapor is the main source of OH. So I will just show you these results for these cases, but my photochemical model contains like 70 different atmospheric cases, and I have results for all of them. I created a web page where you can explore all of my results and different scenarios that I modeled. And you can make interactive plots using this web page to see how the concentration of a specific gas in the atmosphere changes. For example, here I am plotting OH, and these are interactive plots. You can also plot the profiles and see how the profiles change as we have the oxygenation of the atmosphere. So if you are curious about other results, I encourage you to check out my website. This is hosted in this web address at the top. Okay, so all of the results that I have shown you so far are for atmospheres in steady state or equilibrium. But the Great Oxidation Event was a transition that happened over time, and it was likely a dynamic transition. This schematic here shows a compilation of Redox proxies around the time of the oxygenation of the atmosphere. This compilation was made by Gomsley et al. 2017. And you can see the glacial deposits here in blue. And the periods that have low oxygen levels are represented by these white chunks here. And periods with high oxygen levels are represented by these red chunks. So it is interesting that this compilation of proxies suggests that oxygen could have oscillated across the Great Oxidation Event, And it is also interesting that we see that some glacial events have low oxygen levels. So as you saw from my results before, my photochemical results show that cold climates tend to have like less oxygen compared to warmer climates. So this kind of agrees with what we see in this compilation here. So we wanted to see if changing temperature due to these glacial events could help explain why we see these oxygen oscillations in the proxy record. So I created a simulation over time of the oxygenation of the atmosphere using these same like proxy constraints. I kind of put the glaciations in a timeline, and here the time is going from 2500 million years ago to 2000 million years ago. And I used the approximate date of these glacial deposits to create a temperature forcing over time for my photochemical model. This plot here shows temperature in the y-axis and the x-axis is time. So you can see that for most of the time I am keeping temperature at 290 Kelvin, but when there is a glaciation, I decrease temperature to 250 Kelvin, and I assume that the glaciations last for 10 million years. And after the glaciations, I increase temperature to 320 Kelvin to represent a transition to a hot, moist greenhouse climate, and then temperature decreases to 290 Kelvin again. And this pattern is repeated for the different glacial deposits. So I use this temperature forcing over time to see how temperature variability could have affected the oxygenation of the atmosphere in a simulation of the GOE over time. I also have a forcing for the oxygen surface input flux into my model. I am increasing the oxygen input flux into the model linearly over time. And this increase on the oxygen input flux could represent an increase in primary productivity. And here I consider two scenarios. In one scenario represented by the black continuous line in this bottom plot, I consider that oxygen increases linearly over time, the oxygen input flux. But if we have a glaciation, I assume that the oxygen input flux decreases, assuming that primary productivity will decrease during these glacial events. And after the glaciations, I assume that primary productivity increases and the oxygen input flux increases because I am assuming that there will be a lot of weathering and a lot of release of nutrients into the ocean. So this pattern repeats for the different glacial events. This is one of the scenarios. The other scenario represented by the black dotted line here is just a scenario in which I increase the oxygen input flux in my model over time in a linear way without considering the effects of the glaciations. So I use this temperature forcing and this oxygen input flux forcing over time to run a simulation of the Great Oxidation Event over time. And these are my results at the bottom plot. This plot here shows the oxygen surface mixing ratio in my model in the y-axis over time in the x-axis. So we see that in this scenario with the continuous black line, where I am considering the effects of the glaciations on the oxygen input flux, we see that the glaciations are characterized by having low oxygen levels. And this is consistent with what we see in the proxy record. And in the aftermath of the glaciations, we have like these peaks of oxygen. So we see like these oxygen oscillations across the Great Oxidation Event. And in the aftermath of the last glaciations, the oxygen just is stable at post-GOE levels. And yeah, this is kind of consistent with some of the proxies that we see. The other scenario in which I just increase linearly oxygen over time without considering the effects of the glaciations, it is a little different. You can see it here in this black dotted line. And in this scenario, we have some glaciations with high oxygen levels. So I think that this suggests that just the temperature variability associated with these glacial events could be important to try to understand why oxygen oscillated across the Great Oxidation Event. It cannot explain everything, but it may have been important for triggering these oscillations. Now, going back to my research question, does climate variability affected the oxygenation of the atmosphere? My photochemical modeling results suggest that the answer to this question is yes. And in particular, I see that warmer climates have more oxygen and less methane. But why? Why warmer climates have more oxygen and less methane? Well, this is what I think is happening in my photochemical modeling results. If there is an increase in temperature in my model, that leads to an increase in water vapor. And with more water vapor, we have more OH production. And this OH will go and react with methane, depleting methane from the atmosphere. So if the concentration of methane decreases, the concentration of oxygen will increase, so we will have more oxygen. And with more oxygen, we will have more ozone production. However, this gets complicated because OH also reacts with ozone. So this is what I think explains my results. But to be honest with you, I am not entirely sure about this. And this brings me to the last part of this talk, which is is about the atmospheric chemistry of the oxygenation of the atmosphere. So the reason I am not 100% sure if the way I am explaining my photochemical modeling results is right is that understanding the results of complex photochemical models is difficult because of the interaction between reactions in these models. In these models, we typically have hundreds of reactions interacting with each other. So all of these interactions make it difficult to understand what is driving a specific result in these models. And we can see this in a very simple example. So let's consider this system of reactions here that has 4 reactions. And let's say that we are interested in understanding what causes ozone destruction in this system of reactions. By the way, this system of reactions is known as the Chapman mechanism. Sidney Chapman proposed this system of reactions to explain why we have an ozone layer in the stratosphere. There are 4 reactions in this system. The first reaction is oxygen photolysis, splitting the oxygen molecule into 2 oxygen atoms. In the second reaction, we have ozone formation. In the reaction number 3, we have ozone photolysis. And in the reaction number 4, we have ozone destruction. We have the reaction of the oxygen atom with ozone to produce 2 oxygen molecules. So if we solve this system of reaction in a photochemical model, we get an answer like this. This plot here shows altitude in the y-axis and the ozone concentration in the x-axis. We see that this is what this system of reactions, what the ozone layer looks like in this system of reactions. And you can see that this model overestimates the observed concentration of ozone by about a factor of 2, which is, I think, is remarkable how such a simple system of reactions can explain so well the ozone layer. The reason why this system of reactions overestimates the concentration of ozone is that it does not consider the presence of some oxidizing radicals that catalyze the destruction of ozone, like hydrogen oxide radicals, nitrogen oxide radicals, and chloride oxide radicals. These radicals catalyze ozone destruction in mechanisms like this, in which we have OH reacting with ozone, producing this HO2 molecule, and then this HO2 molecule reacts again with ozone to regenerate the OH. So going back to my problem, let's say that we are interested in understanding what causes ozone destruction in this Chapman system of reactions. Intuitively, we could just say, let's look at the reactions that destroy ozone, and let's look for the reaction that has the highest rate, and that will provide the answer that we want. So for example, we see that the reaction number 3 and the reaction number 4 destroy ozone. And we could just see which reaction has the highest rate, and that will be the answer that we want. And this way of thinking makes sense and is sometimes right, but not always. And the problem is that in a system of reactions, like some of the reactions are interconnected with each other. For example, we see that the reaction number 1 here photolyzes oxygen to produce these 2 oxygen atoms, and then these 2 oxygen atoms could be used by the reaction number 4 to destroy ozone. So the effect of the reaction number 4 depends on the effect of the reaction number 1. So you cannot consider the effects of these reactions in isolation. So to solve this problem, we need to connect the reactions, or we need to construct chemical reaction chains or pathways. For example, we can connect the reaction number 3 with the reaction number 4 to create this ozone destructing pathway that uses 2 ozone molecules to produce 3 oxygen molecules. And we can do the same with the reaction number 1 and the reaction number 4. So the solution to this problem is to construct pathways or chemical reaction chains to understand the results of these photochemical models. And Ralph Lehmann, he's a German researcher. He created this beautiful algorithm that can automatically build these pathways for you in a reaction system. And this algorithm can also quantify how important these pathways are to explain a concentration change of a specific species. When I was in the first year of my PhD, I was very interested in using this algorithm to try to understand better my photochemical modeling results. However, this algorithm is not open source. So I had to create my own version of this algorithm from scratch, and I called it ChemPath. ChemPath is a pathway analysis program. This is what this algorithm, what is the name? This is the name of this algorithm. And this is open source. So if you work with photochemical models, you are welcome to use my code. It is hosted here in GitHub. And I will not explain the details of this algorithm. If you are interested in understanding how the algorithm works, I recommend you to read this paper here, where I describe how ChemPath works. This is a preprint. This paper was recently accepted for publication, so I think it will be published like in probably 3 weeks or 1 month. So the basic idea of this algorithm is that it allows you to build these pathways to understand like which interactions of gases is the most important to produce a specific result in a photochemical model. And I think this could be a very good tool to try to understand what is happening in the atmospheric chemistry of the oxygenation of the atmosphere. Because using a tool like this, like we could see which reaction change or which chemical mechanisms are responsible for producing ozone, for example, in the atmosphere, or for destroying methane. And this will be very interesting. And this is what I am working on right now. This is kind of work in progress. I am currently writing a paper on this, so if you are interested in this, stay tuned. But I will just show you some preliminary results. I will show you pathways that produce and destroy OH across the oxygenation of the atmosphere. And like I said before, OH is the main oxidant of the atmosphere, so it is very important for atmospheric chemistry, and it just makes sense to see what is happening to OH across the Great Oxidation Event. So I will show you these preliminary results in plots like this one here. The top plot here shows my simulations of the Great Oxidation Event. This is a simulation over time. This is not a steady state simulation. So we have time in the x-axis, and we have the surface oxygen mixing ratio in the y-axis. I plot different temperatures in different colors. Again, like the Snowball Earth climates are in blue. Temperate climates are in black, and hot moist greenhouse climates are in red. I forced this model increasing the oxygen input flux into the model, and I ran the model over time. So you can see that after about 1,000 years, the atmosphere becomes oxygenated. And we see that after the oxygenation of the atmosphere, warmer climates have more oxygen. In the bottom plots, I will show you the pathways for OH production. The left plot shows altitude in the y-axis and the rate of a specific pathway in the x-axis. And the bottom right plot shows, again, altitude in the y-axis and the contribution of a specific pathway to OH production. And you can think of this contribution as the fraction of molecules that are produced by a specific pathway. And I will show you two pathways for OH production. The first pathway is, I will plot it with these continuous lines. This is not shown in these bottom plots currently, but it will appear soon. And this is just the pathway that I explained before. This is the main pathway for OH production in the modern atmosphere, in which we have ozone photolysis, producing this O1D molecule that can split water vapor into OH. The other pathway at the bottom is a more complex pathway, but the basic idea of this pathway is that it is creating OH via water photolysis, water vapor photolysis. And I show pathways at different points in time, represented by these cross marks in the top plot here. So you can see that at this time, when the oxygenation of the atmosphere is about to happen, the main pathway for OH production is this bottom pathway here that produces OH through water vapor photolysis. And this makes sense because before the oxygenation of the atmosphere, we have not much ozone in the atmosphere. So this top pathway could not be important before the Great Oxidation Event. So OH is being produced by water vapor photolysis. And this makes sense because if we don't have an ozone layer, we have more potent photons reaching the troposphere that have the capability to split water vapor to produce OH. But as we go through the oxygenation of the atmosphere, we see that the other pathway starts to become more important. And when the atmosphere becomes fully oxygenated, this is the main pathway for OH production in the atmosphere. Which makes sense because, like I said, this is the main pathway for OH production in the modern atmosphere. And it is interesting that we see that there is a lot more OH production via this pathway at warmer climates. And again, this makes sense because at warmer climates, we have more water vapor in the atmosphere, so you can have more OH production. Now, what is destroying OH across the oxygenation of the atmosphere? Well, I will show you here this pathway that destroys OH. This is a methane oxidation pathway. that basically uses OH and oxygen to oxidize methane into carbon monoxide. And you can see that this pathway kind of becomes more important as the atmosphere becomes more oxygenated. And it is interesting that at warmer climates, this pathway has a higher rate, which suggests that all of this extra OH that we are generating in these warmer climates is being used to oxidize methane. And that is why we see less methane in these warmer climates. I will show you also a pathway that is producing ozone, because ozone is just such a wonderful gas in the atmosphere, especially if it is in the stratosphere, because in the troposphere it is toxic. But I will show you how the ozone layer forms from the perspective of this pathway analysis across the oxygenation of the atmosphere. So this is the pathway that forms ozone in my models. This is a very well-known pathway. This is oxygen photolysis producing these two oxygen atoms that are used to produce ozone. So you can see that before the oxygenation of the atmosphere, this pathway is not important because we don't have oxygen in the atmosphere. But as the concentration of oxygen in the atmosphere starts to increase, this pathway becomes more important. And then it starts to form a lot of ozone in the stratosphere. So that's all the results I will show you in this presentation. And this is just a summary of my talk. These are the main points. Climate variability likely affected the oxygenation of the atmosphere. Warm climates have more oxygen and cold climates have less oxygen. Constructing pathways can help understand complex chemical models, and quantifying these pathways can help us understand the chemistry of the oxygenation of the atmosphere. And I just want to acknowledge the help of a lot of people throughout my PhD. None of the work that I presented today would have been possible without the help of all the people that I name here. So yeah, that's all, and I am happy to take questions.
Thanks, Daniel. Great work. We'll switch to our question discussion. You can ask your questions either by raising your hand, so find the reactions button on the bottom of your screen and click that, and then the raise hand button is at the bottom. Or you can type your question and I can ask it for you. So I'll give a few seconds for people to formulate their questions.
Hey, Daniel, maybe I start with a question. Very interesting talk. My question is about this long-term kind of progressive increase in organic productivity that you kind of put in your model to drive this oscillations, climatic oscillation. And it's kind of hard for me to see how you would have long-term progressive increase in productivity. I understand for model maybe it's useful, but I'm wondering if you would not have this increase in productivity, if you just sort of created some oxygen and you got into first glaciation and you get out of first glaciation and you increase productivity again, and you oxidize methane and you go to second glaciation. So you kind of get into this cycle of climatic changes. And if I understand your model correctly, maybe one way to get out of this cycle is that the last glaciation maybe ended with extreme greenhouse conditions, and when it kind of let it to increase oxygen to a state that methane would not be a player as a greenhouse gas, and you kind of get into long-term greenhouse conditions and oxygenated state of atmosphere. So do you see any problem with it, or like would it fit to your model, or what do you think about it?
Yeah, I actually have some simulations in which instead of increasing the oxygen input flux into the model linearly, I just keep it constant, and I just do a temperature forcing through the glaciations. And in those simulations, I saw that kind of when the atmosphere is in this kind of not very stable state, just changing temperature could drive these oxygen oscillations. And especially a result that I saw very consistently is that when you go to these hot moist greenhouse climates, you end up with these oxygenated atmospheres because of what you were saying, that you have a lot of water vapor in the atmosphere and producing a lot of OH and driving methane destruction. Yeah, but I think in order to have stable oxygen levels, like post-GOE oxygen levels, I do need some kind of increase of the oxygen input flux. It doesn't have to be gradual over time. Like it could be just like an event that happens suddenly, and there is a sudden increase in the oxygen input flux in time. But yeah, in my model, there needs to be some kind of increase in the oxygen input flux to drive the oxygenation of the atmosphere.
Yeah, I mean, I don't mean that it shouldn't be increase in oxygen. I think increase in oxygen drove the first glaciation, but it could be that system was just in this state that it was ready for transition to oxygenated state, and when just a little kick would be enough to switch it sort of to more oxygenated state and cause glaciation.
I see.
Okay. Paul had a question in the chat from Paul Hoffman. How would glaciation affect atmospheric composition before the GOE?
Well, if we are before the GOE with low oxygen levels, I think it depends. I've seen two different behaviors in my photochemical model, and it depends on where in the model you are. Like if you are in a place where oxygen is not very stable, going into a glaciation, I've seen that in my model can make oxygen levels increase a lot and kind of oxygenate the atmosphere. However, if we have an atmosphere that is stable at low oxygen levels, just going into a glaciation doesn't seem to affect much oxygen before the Great Oxidation Event. And I think what is happening there is, again, the key factor for the atmospheric chemistry, at least, is what happens to water vapor and oxidizing radicals as you go through a glaciation. So in colder climates, there will be less water vapor in the atmosphere and less oxidizing radicals. If you have an atmosphere that is stable at low oxygen levels and you have less oxidizing radicals, you will probably have less oxidation, and that will probably not change much oxygen because you already have very few oxidation because of the low oxygen levels. But if you are in a place where oxygen is not very stable, I think that having less oxidizing radicals and having a little less oxidation will mean that you are using less oxygen to do this oxidation. So if you have less oxidation, that could make oxygen increase to these post-GOE levels. And that's something I've seen in my model sometimes.
All right, thanks, Daniel. Marguerite, you ready to go? Please go ahead.
Hi, can you hear me?
Yeah.
Great talk. I have to check out the website also. I was wondering, have you considered modulating the effect of astronomical climate forcing or variability having an effect on both global temperature and also marine oxygen production, as we know from studies of the more recent past and some of my own work on the GOE. Yeah, and can you make any predictions about whether this could potentially have a similar effect given the shorter timescales that we're talking about than the glaciations you were talking about?
Yeah, I haven't considered the effect of temperature on the oxygen flux itself. I think that that's something that is important to work on. And yeah, in terms of predictions, yeah, I'm not sure what will happen to primary productivity, like at different temperatures. Like in one of my modeling over time, I was assuming that if you have an increase in temperature on long time scales, that could lead to an increase in the oxygen input flux because you will have more weathering. But in terms of these short time scales of respiration and photosynthesis, I'm not sure how changing temperature will increase or change the fluxes. Like I've heard before that maybe if you have an increase in temperature, the rate of respiration will increase, and maybe that could affect the flux. But yeah, probably you will need some kind of model of metabolism and how temperature affects metabolism to get that answer.
Yeah, just so we have this one paper in EPSL by myself, Margriet Lantink, in 2023, and also there's a new paper coming up in chemical geology where we looked at Banadine formations, and from that we reconstructed fluxes of oxygen, marine oxygen production, which could periodically peaking above 15 millimole per square meter per let me check year. So I was just curious. Maybe we can reach out later about this, but what kind of effect that could have
Yeah,
on the
very
atmosphere
interesting.
chemistry. Yeah. But the basic idea is that astronomical forcing periodically increases the marine carbon burial and primary productivity by supplying nutrients, etc.
Yeah, I will be interested to
Okay,
see
great.
how those processes affect my model.
Thanks.
Okay, thanks, Marguerite. All right, no more questions right now. I'll give people a moment to speak up if they would like. All right, well, thanks, Daniel. That was a great presentation and really good discussion at the end.
Thank you.
And thanks everybody for being here. Next week we have a presentation from Terry Eson. So come for that. And until then, everybody take care. See you guys.
Bye.